All right, hello everyone. My name is Emily. I'm an associate R&D engineer on the bioengineering platform. I've been here for around 2-ish years now. And today I'm going to talk to you about something that I work on every single day, which is designing electronics for instrumentation control. So before we can think about, okay, how do I control an instrument, we have to think about what actually goes into an instrument. And so this is what you might experience when you walk up to anything in the lab. I'm using the Sony fax because I'm kind of biased towards that. But this goes for any instrument that you use in the lab, like the light box for imaging your gels or Spectromax, for example. You have the instrument on the side over there, and then you have this computer or some software that you run. Like you'll open up the Sony fax software, and then you'll tell it, okay, can you sort my samples? And the instrument will start doing a bunch of things. But how does it go from your commands on the computer and the software all the way to the instrument? Well, it seems a little bit like magic, but it's not magic. It's just electronics. So in the software, the electronics just kind of take the messages from the software and translate that into some hardware component on the instrument. So on the computer, if you say something like, I want you to sort my samples into well A1, the electronics will take that message from the computer. It'll go over to the instrument, and it'll say, okay, they want to sort into this specific part on the plate. So it'll take the stage right here, it'll move it to the specified position, and then it'll do exactly as you say. And so that's pretty common for a lot of different instruments. I'm not sure if you've heard yet, but the Biohub team is building this label-free malaria scope. Very cool. I'm going to use it as a case study throughout this entire presentation, since everyone, or for the most part, everyone is very familiar with it. And so we have this very portable instrument that looks at whole red blood cells. And it comes with its own computer, except it's actually integrated onto the instrument itself. And the computer that we use is a Raspberry Pi. It's a very popular open source computer. And it runs all the experiments that you need on the label-free malaria scope. And just to kind of go through the different types of functionality that the malaria scope has, it has power, because every instrument needs power. It has a motorized focus mechanism to keep your samples in focus, a UV LED to excite your sample so that you can actually see your red blood cells, some flow control so that you can control how much of your sample actually flows through and is seen by the microscope. And then you have some under the hood things that make it all work, like these interlock switches, fans to keep it all cool so that the electronics and everything is happy. And then you have some user nice to haves, like a touch screen and a focus adjustment knob. So there's a lot of stuff that goes under the hood of all these like boxes of instruments that you see. This is just like a final shopping list of all that different functionality that it has. And that's kind of a lot of stuff. One, how do you make this all happen? Like if you say, I want to turn on the LED, how does that actually happen? And how do you make it such that the computer actually understands what to do? Once again, the answer is electronics, but how do you build those electronics? If you've taken a basic electronics course, this might be kind of familiar. You have these breadboards with a bunch of chips that do stuff, and then you jumper everything together, and then you get this hot mess. But if you're shipping 20 instruments all the way to another country, this mess isn't going to really work out well for you. It'll be a nightmare building it. It'll be a nightmare making sure that all your connections are secure. So what an instrument really needs is a printed circuit board or a PCB. And we've kind of done plenty of these for different types of instruments and projects. I'm just going to go through some examples here of ones that I've worked on the Biohub team, but it's not a fully inclusive list. There's plenty that other people on the team have built. So for the fax automation, we're automating manual tasks that an RA does during fax sorting, which is vortexing the tube before they sort and also keeping the samples on ice. So in this little corner, you see this board I have. It actually has 18 motor drivers, which agitates 18 tubes prior to sorting, and that's all automatically scheduled. You don't have to do anything like, hey, spin this motor. And it also has temperature control for the tube housing to keep it at 4 degrees Celsius via some temperature sensors and some pneumatic valve control. We actually have a second board for the fax automation, and it has these little white chips that you see up here. And these are actually encoders that detect the position that the tube is in and stops it exactly at the same place. So that increases the reliability of tube pickups by the robotic arm, because if you drop a sample, that's not great. There's this other board. We have a low-cost fragment analyzer. I didn't actually build this board. Andrew Cote did. He left about a year ago, but I took it on afterwards. And it does all the things that your standard gel box does. which is generating a variable high voltage for gel electrophoresis. It also has current monitoring for fault detection. And then, as I mentioned before, the label-free malaria scope. And this PCB has all the capabilities that I talked about earlier. But how does it actually do all of that? To kind of dig into that, we need to look at the PCB anatomy. A PCB just connects things together. That's really all it does. And to understand how it does that, we have to look at the cross-section. And if you remember anything about how a PCB is made, it's really just a copper sandwich. So this is just one layer of it. I kind of have an exploded view of this circle section right here. So the stuff you see in white, like this little half box right here, is called a silk screen, and you use that to label your different components. Most of your board will be covered by what's called a solder mask. In this picture, it's purple, but you'll probably be familiar with the ones in green. And where all the magic happens is in the copper right here. It's electrically conductive, and that allows you to take a signal from point A to point B. And that kind of sits on top of a fiberglass core. So you'll notice in this cross-section, only specific areas have copper, and those are called traces. And they are the highways in which your signals will travel from one place to the other. And this is an open face sandwich, but we can close up that sandwich with a 2-layer PCB. So you actually see the sandwich here of copper, fiberglass, and then another layer of copper on the back side of the board. And what a 2-layer PCB enables you to do is have these vias. They're like the copper vertical tunnels. They're just holes filled with copper that take your signal from the front side all the way to the back side. And that just allows you to have more room for routing, more room for connections, higher density, what have you. So you can keep going. You can keep stacking them up all you want. You can make as big of a sandwich as you want at a cost. So we love 4-layer PCBs. They're great for doing your basic functionality. You have the top level copper here, bottom level copper here, and 2 internal planes right over here. And that's all sandwiched between some fiberglass. So now that we know how a PCB is made, and we kind of know, okay, the copper is manipulated in these different ways to connect different components, let's talk about the components that make these connections actually meaningful so you can do something with it. So this is just a very specific corner of the malaria scope board. I'm just going to point out the different components here. In the pink and the blue, we have resistors and capacitors. These are your very basic circuit elements. They're called passives collectively, and they're not super interesting, but they're very important. The purple is showing integrated circuits, and these are literal black boxes. They're very tiny, but they pack a punch. So just for scale, this U5 element right here in purple, U5, is a temperature and humidity sensor, and it's probably like 6 millimeters by 6 millimeters. Whenever I work with it, I have to be super careful because I could like literally blow it off my finger and just lose like $7 right there. But they do a lot, and a lot of the rest of the components on these boards, like all the resistors, all the capacitors, they're there to actually interface with the integrated circuit to make sure that it works. But as far as interfacing with other components away from the board, like your motors, your LEDs and whatnot, you have connectors. And connectors, much like other components, come in 2 different packages, surface mount and through hole. So this gray one right here, it sits right on top of the surface mount. Oh, whoops. And then you also have through holes, which is on this right-hand side here. And through holes are quite bulky, so you don't see them as often, but they're useful because they're mechanically robust, they deliver more power, and they're just a lot easier to prototype with. So we can talk, now that we know like these components, we can connect it back to the PCB anatomy. So in light green here, you see these traces, and this trace is going from like this blue test point right here. You travel to this first pin here, and then you go to this hole, and these holes are the vias. This is kind of like a top-down view of a PCB. I've kind of just highlighted it here, and you just kind of extend that to the rest of the board. All right, so now we know how to make a PCB, and now we can make it in 6 very easy steps, and emphasis on the quotation marks. So the first step is kind of speccing your parts. You want to find parts that actually have the functionality that you're looking for, and then once you spec all those parts, you do a schematic drawing, which kind of shows how everything gets connected together. Then you'll define your board shape, you'll import, sort, and place all of those components onto the board, and then you just connect everything together and you have a board. So let's walk through that process for the malaria scope. Before I do that, this is some software that you can use to do all of that circuit layout software. So there's free ones, and then obviously there's ones that cost a lot of money. We like KiCad because it's free and it's an open source. It has a really great open source community, so it's well supported. All right, so the label-free malaria scope. Once again, here's all the different functionality that it's capable of. And this kind of list just translates to a lot of different integrated circuits that need to be spec'd out with the right requirements and the right functionality to make sure that it's doing the work that you need it to do. Just as an example for how we spec different parts, this is a motor that we use for that stage focus adjustment part. And we use this motor to kind of move the stage up and down to keep your samples in focus. And we're gonna read the data sheet because we always read the manual when we get new stuff. And here we can see that it's a bipolar stepper motor, and the power you need to make it run is 12 volts, and an input power of 2.5 watts is required. That roughly translates to 200 milliamps. So our requirements for this driver is that it has the right power requirements, as I mentioned, and it actually works with the type of stepper motor that we have. To make our lives easier, we want a simple communication interface. Like if we tell it go, it will just go. And we also want adjustable step resolution. For example, if you want to go from coarse to fine adjustment or focus. And this is very important and non-trivial, but it needs to be in stock. More on that later. So I go onto my favorite electronics distributor, DigiKey Electronics, and I find the perfect chip for me. It's bipolar, it has all these different step resolutions, it has more current output than I actually need, and our voltage is right within this range. So it looks perfect, and you just kind of rinse and repeat that for the rest of the items on your shopping list. And then once you spec out all your parts, you look at the synergy of them together, like do they work well together? Are they all like on the same power that I have on my board? All right, so you finally have all your parts. I can show how they're all connected together in a schematic drawing, and this is kind of what it looks like. On the left-hand side here, we have the Raspberry Pi. In the middle here, we have the power management. On the right-hand side, this is what the chip for the motor driver that I just talked about looks like. And you just keep doing that for every single thing. So it can be kind of complicated, so organization is really key here. Once you're sure everything is connected right, then you can define your board shape. And the important thing here is that your board needs to mechanically fit onto the instrument, otherwise, why are you building it? So you need to consider size and shape. And actually in this board, I have 4 different boards here. That's just how much functionality the malaria scope has. The one on the left here, this big one, is the main one that does a lot of the legwork. And then we have kind of 3 peripheral ones here that look like little growths out of the board. And I'll talk a little bit about those later. All right, so you have your board shape. You're gonna now import all the parts that you defined in your schematic drawing, and it kind of imports in mass, and you're like, oh God, there's so many things to connect. But then you'll sort them out, and you're like, okay, this looks a little more manageable. And you wanna sort them into different modules. This is kind of how I sorted it. So for example, for devices with the same communication, they're probably gonna have the same signal that's routed to them, so I wanna keep them like close together. So now that you have it in modules, you can place it onto your board. Just for reference here, everything in red is the front side of the board, everything in green is the back side of the board, and everything in yellow is kind of holes that go through the entire board. And there's a famous online saying that PCB design is 90% placement and 10% routing, and I found that to be like very true every single time. If you have crappy placement, like you're gonna make your life a nightmare because it's just unnecessarily difficult. For example, if you have a component here and it connects to something all the way over here, you're just gonna have one long trace that goes all the way across your board, and it's just like disruptive. So you wanna place it in a way that makes your life easier, the connections are nice and short, and they make a lot of sense. So once you place it in a way that makes you happy, you're gonna just connect it all together. This was my final routing, but in reality, you kind of go back and forth between placing parts and routing. It's really like a complicated sort of puzzle of fitting stuff together and putting them in the most optimal place, because when you route something, you might realize like, oh, I should have moved this a little over to the left. Some people actually think apparently that I'm playing a game at my desk when I'm doing this, which I get, it's like super colorful. And it is kind of a game. It's a lot of fun to kind of figure out where the right position will be and what will make your life harder or not. All right, so now everything's finally connected together and you have this beautiful board layout. Ta-da! Yay. Okay, so just one last check before you send it off for fabrication. You need to check that it actually fits onto the instrument one last time. So this is the fitting on the Raspberry Pi. The screw holes are in the right place, yay. Everything over here, it doesn't interfere with this bottom plate right here. And you can plug everything in the right place. For example, if I had this connector right here, there would be no red flags if I just looked at this. But when I look at it on the whole instrument, I'm like, I have no room to plug things in. So this all looks good. You're gonna fabricate your board. You send it out to some house. You're gonna simply assemble all of it together and plug it into your microscope, and it's gonna work beautifully because you are a great engineer. Usually that will happen maybe on like the third revision of your board. I just spun out my third revision of some board, or this board actually. So now that I've kind of gone over the steps, I'll tell you all about the challenges that go through this six-step easy process. So I hinted at this earlier. These are my 4 favorite words as of 2020. Global supply chain issues. I mean, you just can't get your hands on anything these days. And I think this picture says a lot. The ship date for this motor driver is in 30 years, y'all. So I will see you all in 30 years. We'll have them shipped out by then. Obviously, that's not plausible. So there's 2 realistic solutions that you can have. Just be proactive, just anticipate your need and just buy everything out before other people buy it out. But obviously 30 years is a very prescient situation. I'm 24, so it doesn't really work out. The second solution is just to scope out proper replacements. It might not be the same exact chip that you wanted. It might have like a little different functionality, but you can still make it work for you. And the third solution is just being resourceful. And I actually have an example for that that's really fun. For the malaria scope, we had this UV LED that's mounted on this PCB right here, and it was out of stock as of last November 2021. And that's obviously really bad because we need the UV LED to actually see the red blood cells, and without this LED, like there's no microscope, right? So we're like, oh no, what should we do? Well, this LED is widely available. There's plenty of LEDs out there that will emit the same exact wavelength that you need. So here it is right there. There's 1,000 of them in stock, which is great for us. And so we just made our own PCB. So that was one of those little peripheral boards that you saw growing out of the main PCB. So we mounted it right here. You see this white silk screen that shows the alignment feature for it. It's a lot cheaper. There's tons of it in stock. If not this one, there's plenty of else out there. And you have more control over the mechanical fitting, which will make people like Chris, who designs the mechanical parts of the scope, a lot more happy. So we had just,
did you buy?
What? Sorry, what?
How many did you buy?
We only bought 20. Sorry, Sandy's question was how many did we buy? We bought 20, and 1,000 could easily be wiped out by like a medium-sized company, but we think we'll be okay for now. Knock on wood. We should have, we can buy plenty more. So yeah, we were really happy with the solution. It was really great and simple. So let's say you get all your parts. That is a challenge in of itself. And now you have to think about actually how do you lay it out. So there's a lot of different chips, as I said. We had temperature, humidity sensors, we had drivers, and all of them kind of have their own specifications of how they want it to work. These are 3 different examples of different types of layouts. So you might have high-speed design, where the trace lengths need to be the same exact length. You have mixed signal with analog signals and digital signals, and you kind of want to separate them because you don't want your digital signals messing up your very quiet, possibly analog signals. And then you also have RF and microwave boards where you have these really large exposed copper areas to kind of minimize interference coming in or out of the board. So let's just go back to what we said earlier. A PCB just simply connects components together. And so if that's the case, then the goal for your layout is to kind of maximize your power or signal integrity. You want to give it the best chance it can to get there safely and not let any unwanted signal or noise kind of couple into your signal. So most chips, as I said before, will have their own layout specifications in the manual, which you will read. But these are just some general tips that I have for helping out with that. So thicker traces are needed for higher power requirements. You can see here that this 12 volt is a lot thicker than this LED indicator signal right here. And it's kind of like trying to stick an elephant through like a straw. It's just not going to work out. It doesn't have that type of capacity. In the same way, your trace width, if it isn't large enough, won't have the type of capacity to carry your current all the way through, and it might dissipate as heat, which is bad in other ways. So just have a thick enough trace for your power requirements. There's a bunch of calculators out there to do that easily. You also want to use power and ground planes to minimize your return path, and that just minimizes the amount of interference that's introduced into your signal. Everything in pink here is just copper, and we just kind of link that to power or ground. And that'll make your routing easier, and it'll make your board a lot cleaner. The last tip I have is to increase your spacing between traces on the same layer. So as you can see in red, these traces are pretty far apart. And then also minimize overlap between traces on different layers. So right here, I have them at like 90-degree angles, so they overlap very minimally. And kind of the analogy I have for this is if you have a really noisy neighbor right next door, you're gonna hear a lot of that noise. So you're like, why don't I just move 5 doors down? Well, the noise is a lot quieter. It might still be there, but at least it's not interfering with you as much. And it's kind of the same situation here. All right. So you have layout within the PCB, and you have actual layout of the PCB and how it interacts with your whole instrument, because that's the whole point of this, right? So we actually formed the main PCB board to be a hat for the Raspberry Pi. And hat stands for hardware attached on top, but it also sits on top of the board like a hat. So that was a really convenient thing for us that kind of minimized the footprint of the board. And then as you can see, there's this little gap between these pins here, because we used extra long headers, and that's just so that we have space for the cooling airflow to flow above the Raspberry Pi, which is doing a bunch of expensive computations and is heating up. That cooling airflow takes that heat away. And then obviously on the instrument itself, you want it to be low profile connectors so it doesn't interfere with like the enclosure that goes right over here. So generally speaking, just a really convenient footprint for the whole PCB. All right, so you have your board laid out. It's finally here. It doesn't work. Oh my God. So this is one example that I have of the board not working. This was actually on the second revision of my board. Fair warning for any epileptic people. It's a bit of seizure inducing. We had this LED flickering issue. We weren't really sure why this was happening. And obviously that's really bad for a microscope where you need a constant light source. It's like, okay, yeah, it's really bad. So when you have problems on your PCBs, the best thing you can do is retrace your steps. So you're looking at the output, you're like, oh God, that's really bad. So you kind of go back to the beginning and think about where it all went wrong. So whoops, playing again, let me pause that. So the LED driver takes in an input signal called a pulse width modulation signal, or PWM signal. And this is a way to deliver an average or varying amount of power to your load, which in this case is the LED. So for example, 50% duty cycle means that it's on 50% of the time. You can see like on and off and then on. And so this will deliver an average of half the power to your load. If it's 100% duty cycle, it'll be on the entire time and it'll deliver the full power. All right, so we take our oscilloscope and we kind of probe those signals. We're looking at the LED current, which is the output of the signal here. We're looking at the PWM signal. You can see one pulse here. And then you can kind of ignore these artifacts. These are measurement artifacts on kind of the edges of this square wave. But you're looking at this blip right here, and it corresponds weirdly well with this blip right here. And it goes to say for anything, if you have poor inputs, you're going to have poor outputs. That's just a universal law. And so we were kind of wondering, why are we getting a poor input? We're taking this PWM signal directly from the Pi. We're not generating it or anything. It just goes straight to the driver. Weird. And this was only happening on one of 3 microscopes, which is especially weird because the PCB assemblies tend to be pretty consistent. And so if it was a problem with the PCB, it would happen across all of the microscopes. Well, it was a really esoteric problem, but we found it on a specific revision of the Raspberry Pi 4B in which the hardware kind of changed a little bit, and that just broke the software. So we actually had a workaround to just use a different software library in which this did not break. So we're back in business. But this goes to say that troubleshooting is important on your PCB. Your PCB will have problems, but it can also be other components that you're interfacing with, especially open source hardware, because open source things tend to have bugs, but if you have a strong community, then those bugs will become more manageable. All right, you finally have a working board. That's great, but now you need to build 20 of them, and you don't want those boards to be difficult to build. If you have to custom make a bunch of cables, you're going to be sitting there for like a day just for one component. So you want to think about how do you make your builds as painless, reliable, and clean as possible. And usually it's not a problem with the PCB itself, but it's usually how you interface with different components on the instrument. For example, how do you connect the motor to the board? So I'm just going to go through a quick case study here. This is one side of the PCB. You can see it's kind of a mess of wires right now. It could be worse, but it is still kind of a lot. We have this little daughter board, which is another one of those little peripheral boards that I showed you earlier. And it's kind of nice because it takes all of the components on this side and takes in the connections right there instead of going straight to the PCB. So it's nice because it minimizes the wire length, but you still have 17 wires. And if a human is hand assembling these wires, they will each introduce a point of failure in assembly. And if you multiply that with all the components that we're making, a human is going to mess something up for sure. And on top of that, if you have connectors that are kind of touch and go, they might slip out. If you bump over a hill or something, then that's really bad too, especially for a portable microscope. So you're going to need some robust connections, and you're going to need good wire management. So for these wires, we actually changed them all to be pre-assembled wires. So no human needed, just machines, and that'll work out great for us. And all these 17 wires get transferred into this nice singular flexible cable that just goes and plugs into the main PCB. And that'll be really great for us because we don't have to hand assemble anything. And then you have this latching connector that firmly places the connector there. So if you bump over hills or you have weird terrain, you won't have to worry about it. So your board is finally ready for production, and you know how to take a PCB from prototype to production. And that all goes to say that PCBs enable instrumentation. They can do a lot of different things, and they can do great things for you, but they require a lot of careful consideration. I just want to thank my team for all their help reviewing all my boards, and the collaborators who give us the opportunity to make cool boards like this. And operations, because I've messaged them plenty of times, like, there's only 30 left, can you please order right now? They have been very essential to this process too. Thanks for listening.